This is SpaceTime Series 21, Episode 53. Coming up on SpaceTime, the interstellar asteroid that may actually be a comet. Japan's Hayabusa 2 reaches its target, the unexplored asteroid Ryugu. And Europe's new Ariane 6 launcher gets the green light. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
A new study suggests Oumuamua, the first interstellar object discovered in our solar system, may be an interstellar comet rather than an asteroid. The findings, reported in the journal Nature, are based on observations by both ground and space-based telescopes showing the interstellar visitor is moving away from the Sun faster than expected. Oumuamua, the first interstellar object discovered in our solar system, has been the subject of intense scrutiny ever since it was identified by the Pan-STARRS telescope in Hawaii back in October 2017. By the way, the name Oumuamua means scout in Hawaiian. Observations of Oumuamua indicate it's an elongated, tiny object whose colour is very similar to that of a comet. Now, by combining data from the European Southern Observatory's Very Large Telescope with NASA's Earth-orbiting Hubble Space Telescope and other observatories, astronomers determined the object's moving away from us faster than predicted. Mind you, this gain in speed is very tiny, and Oumuamua is still slowing down because of the gravitational pull of the Sun. But the thing is, it's not slowing down as fast as it should be, as predicted by celestial mechanics. Scientists have investigated numerous scenarios to try and explain the faster-than-predicted speed of this peculiar interstellar visitor. The most likely explanation is that Oumuamua is venting material from its surface due to solar heating, a behaviour known as outgassing, which is typical for comets. The thrust from this ejected material is thought to be providing a small but very steady push, sending Oumuamua hurtling out of the solar system faster than expected, now travelling at over 114,000 kilometres per hour. The study's lead author, Marco Micheli from the European Space Agency, says the outgassing contradicts the previous classification of Oumuamua as an interstellar asteroid. Instead, he thinks it's probably a tiny weird comet, and that view appears to be supported by the fact that the boost appears to be getting smaller the further it travels away from the Sun, again, something typical of comets. However, all this doesn't explain one really important aspect. Usually, when comets are warmed by the Sun, they eject dust and gas, which forms a cloud of material around them called a coma, and they also produce those two characteristic cometary tails. However, the authors could not detect any sort of visual evidence of the outgassing. Now, they think that could mean that Oumuamua is venting very large, coarse dust grains. They speculate that perhaps the small dust grains adorning the surface of most comets have been eroded away during Oumuamua's long journey through interstellar space, and so only larger dust grains are remaining. They say a cloud of these larger particles wouldn't be bright enough to be detected, and it would explain the unexpected change in Oumuamua's speed. Because that raises another problem. We have lots of comets coming from the Oort cloud, which is also partially in interstellar space. And those comets would have been on journeys lasting the same amount of time as Oumuamua's, yet they still become visually identifiable as comets when they get close enough to the Sun. Not only is Oumuamua's hypothesized outgassing an unsolved mystery, but also its interstellar origin. The authors originally performed the new observations on Oumuamua to exactly determine its path, in order to work out where it's come from. However, the change in velocity they discovered means its true origins may now remain a mystery. You're listening to Space Time. I'm Stuart Gary. Well, after a journey lasting 3.5 years, Japan's Hayabusa 2 spacecraft has finally reached its target, a kilometre-wide near-Earth asteroid called 162173 Ryugu. JAXA, the Japan Aerospace Exploration Agency, says the probe's now about 10 kilometres above the desolate asteroid's boulder-strewn surface. Ryugu is classified as a C-type asteroid. C-type asteroids are thought to be rich in carbon and have a composition similar to that of the early solar system. Part of Hayabusa 2's mission is to determine if the dark appearance of Ryugu's surface is due to it being rich in carbon or because of small metallic particles such as magnetite. By studying the chemical and isotopic analysis of this asteroid's composition, scientists will not just understand this asteroid better, but they'll also learn more about the origins of the Earth and its water. You see, the isotopic composition of water found in many meteorites suggests that they, rather than comets, are the most likely source for much of Earth's oceans. Ryugu circles the Sun every 474 Earth days in an elongated orbit ranging from 0.96 to 1.41 astronomical units, inclined at about 6 degrees to the ecliptic, Earth's average orbital plane around the Sun. An astronomical unit is about 150 million kilometres, or 8.3 light minutes. It's the average distance between the Earth and the Sun. One of the first things Hayabusa 2's measured was Ryugu's rotational period, that is, how fast it spins on its axis. And it turns out a day on Ryugu lasts about 7.5 hours. By the way, the name Ryugu? Well, it's Japanese for Dragon Palace, a magical underwater palace in Japanese mythology. It's said a fisher travelled to the palace on the back of a turtle. And when he returned, he carried with him a mysterious box, much like Hayabusa 2, returning with samples. The 600-kilogram Hayabusa 2 was launched aboard an H-2A rocket from the Tanegashima Space Center south of Tokyo in December 2014. The mission follows on from the original Hayabusa spacecraft, which explored the asteroid Itokawa on a sample return mission in 2005. Hayabusa 2 is based on the original Hayabusa design, but it uses upgraded guidance and navigation technology, as well as more advanced antennas and attitude control systems. The ion engine-propelled probe carries multiple scientific payloads, including remote sensing optical navigation, near-infrared and infrared thermal cameras, as well as light detection and ranging LiDAR instruments. Hayabusa 2's sampling system will be similar to that employed by the original Hayabusa. The spacecraft will approach the surface of the asteroid with a sampling horn. When the horn touches the surface, it'll trigger a 5-gram titanium bullet projectile to be fired at 300 meters per second. The resulting ejector particles will then be collected by a catcher at the top of the horn. Hayabusa 2 will also collect samples from deeper below the surface, which haven't been subjected to space weathering. Of course, this will require removing a larger volume of surface material, meaning a more substantial impactor. In this case, they'll be using a 2.5 kilogram copper projectile as an impactor. The impactor will be contained in a 4.5 kilogram shaped charge of plasticized HMT, an explosive, which will be launched from an altitude of about 0.5 kilometre. Now, once the impact is launched, Hayabusa 2 will maneuver itself to the far side of the asteroid to avoid debris from the explosion. About 40 minutes after separation, the device will explode, driving the copper impactor deep below the asteroid's surface. Hayabusa 2 will wait about 2 weeks for debris to clear from the impact site. It will then descend into the newly formed crater to retrieve samples. The spacecraft slated to depart the asteroid in December 2019 and return samples to Earth in December 2020. And like its predecessor, those samples will be parachuted back down to the Earth's surface on the Oh-MOO-ah rocket range in outback South Australia. Hayabusa 2 is also carrying 4 small lander rovers, which will explore the asteroid's surface and provide context information for the return samples. They'll be deployed from the spacecraft at altitudes of about 60 meters, free-falling down to the surface under the asteroid's weak gravity. 2 of the rovers will be deployed in a landing canister known as Minerva 2-1. These are identical 1.1 kilogram rovers shaped like cylinders. They'll move across the surface simply by tumbling in the low gravitational field, using a torque generated by rotating masses within the rover. Their scientific payload will include a stereo camera, a wide-angle camera, and a thermometer. Solar cells and double-layered capacitors will provide electrical power. A second landing canister, Minerva 2-2, holds a third rover, which is shaped a little bit like an octagonal prism and about 1 kilogram in mass. It's designed to hop across the asteroid surface. It's equipped with 2 cameras, a thermometer, an accelerometer, and both optical and ultraviolet LEDs for illumination to detect floating dust particles. Now, the fourth of the rovers is much larger. It's the Mobile Asteroid Surface Scout, or MASCOT. It has a mass of 9.6 kilograms and carries an infrared spectrometer, a magnetometer, a radiometer, and a camera. It's designed to image the small-scale structure, distribution, and texture of the regolith on the asteroid's surface. It'll tumble itself across the surface to position itself for measurements, investigating the surface structure, mineralogical composition, thermal behavior, and magnetic properties of the asteroid. I'm Stuart Gary. This is SpaceTime. The European Space Agency has given a green light to the latest design for the new Ariane 6 launch system. The 63-metre tall Ariane 6 will eventually replace the current Ariane 5 as Europe's primary heavy lift launch system, providing the same lifting capacity but at significantly lower cost. The Ariane 6 will feature a new simplified version of the existing Ariane 5 Vulcan 2 rocket engine. It'll initially continue burning cryogenic liquid hydrogen and liquid oxygen, but could eventually replace the liquid hydrogen system with liquid methane instead. The Vulcan 2.1 will also use a more precise laser rather than electrical ignition system and include the use of 3D printed components. One of the key aspects of the new launch system will be the use of either 2 or 4 core stage SRBs or strap-on solid rocket boosters, depending on payload requirements. The Ariane 5's existing SRBs, which shared significant technology with the core stage of France's M51 submarine-launched ballistic nuclear missile, are being replaced on the Ariane 6 by a new bigger design known as the P120C. The P120C will also be used as the core stage for the Ariane Vega C rocket. Fitted with 2 P120C boosters, the Ariane 6-2 version will have a launch mass of around 530 tons and will be capable of lifting up to 11,000 kilograms into low Earth orbit and up to 5,000 kilograms into geostationary transfer orbit. However, with 4 P120C boosters, the Ariane 6-4 version will have a lift mass of around 860 tons, carrying 21,500 kilograms into low Earth orbit and up to 11,500 kilograms into geostationary transfer orbit. In place of the current Ariane 5's upper stage HM7B engine, the Ariane 6 upper stage will use a Vinci rocket engine, burning cryogenic hydrogen and liquid oxygen. This new vacuum engine will be designed to restart at least 5 times. The European Space Agency and its commercial arm Arianespace expects to launch up to 12 Ariane 6 missions every year, with a maiden flight of the new design currently slated for 2020. I'm Stuart Gary. You're listening to SpaceTime. And time now to turn our eyes to the skies and check out the celestial sphere for July on SkyWatch. July is the 7th month of the year in both the Julian and Gregorian calendars. It's named after the Roman Emperor Julius Caesar, who was born in that month. Prior to that, it was simply called Quintilis, Latin for 5th. On average, July is the warmest month of the year in the Northern Hemisphere, which is experiencing summer. Of course, conversely, that means it's also the coldest month in the year in the Southern Hemisphere, which is experiencing winter. And it also marks the time when Earth reaches aphelion, its furthest orbital distance from the Sun. Seasons aren't dictated by the distance from the Sun, but rather the length of the day, and hence the amount of sunlight any given part of the Earth's surface receives, and that's governed by the tilt of Earth's axis. During this year's aphelion, Earth will be at a distance of 152,095,566 kilometres from the Sun. That's about 5 million kilometres further away than what it is during perihelion. And for 2018, aphelion will occur on Saturday, July the 7th at 2:46 a.m. Australian Eastern Standard Time. That's 12:46 p.m. on Friday, July the 6th, US Eastern Daylight Time, and 16:46 in the afternoon of July the 6th, Greenwich Mean Time. Okay, let's turn to stars other than the Sun now, and the Southern Cross is at its highest point in the southern sky this time of year, pointing directly to the southern celestial pole. The Southern Cross is within the constellation of Centaurus the Centaur, the half-man, half-horse of Greek mythology. The creature is holding a bow loaded with an arrow, and the Centaur's front leg is marked by the 2 pointer stars, Alpha and Beta Centauri. At 4.3 light-years, Alpha Centauri, the second of the 2 pointer stars from the Southern Cross, is also the nearest star system to the Sun. The Centaur's back arches over the Southern Cross, and just above this is Omega Centauri, a spectacular globular cluster easily visible with the unaided eye from dark locations. Globular clusters are tightly packed spheres containing thousands of stars, all originally born at the same time from the same molecular gas and dust cloud. Omega Centauri is about 16,000 light-years away. It's one of the largest and brightest of the many globular clusters known to orbit around the Milky Way galaxy. Centaurus was also included among the 48 constellations listed by the 2nd century astronomer Ptolemy, and it remains one of the 88 modern-day constellations. Okay, let's turn to the right now, that's the west, and we'll see the constellation Leo the Lion just above the western horizon. Its brightest star Regulus, or the Little King, is located 79 light-years away. Regulus, designated Alpha Leonis, is actually a 5-star system organised into 2 pairs. Regulus A is a spectroscopic binary comprising a spectral type B blue-white main sequence star, 4 times the mass and some 288 times the luminosity of the Sun. Its faint companion is thought to be a white dwarf, the stellar corpse of a Sun-like star. Spectroscopic binaries are stars which can't be resolved by optical telescopes into 2 separate objects, and so can only be separated by observing their spectroscopic Doppler shift as they orbit around each other. Located a bit further away are Regulus B, C, and D, which are all dim main sequence stars. At the opposite end of the constellation from Regulus is the star Beta Leonis. It's also a luminous blue-white star, thought to be a spectral type A, about half as bright as Regulus, and the 3rd brightest star in the constellation Leo. Beta Leonis has about 1.8 times the mass of the Sun, and about 15 times the Sun's luminosity. It's suspected of being a dwarf Cepheid or Delta Scuti type variable star, meaning its luminosity varies very slightly over a period of several hours due to pulsations on its surface. Next we see Algebra or Gamma Leonis, a bright binary system with a visible 3rd component. The 2 primary stars are located about 126 light-years away and can be resolved in small backyard telescopes. Both are yellow-gold giants, orbiting each other every 600 Earth days. The unrelated tertiary star, named 40 Leonis, is a yellow tin star which can be seen through binoculars. The system's traditional name, Algebra, means the forehead. The next star in the group is Delta Leonis, or Zosma, a blue-white star some 58 light-years from Earth. Then there's Epsilon Leonis, a yellow giant some 251 light-years away, and Zeta Leonis, an optical triple-star system, the brightest component of which is a white giant some 260 light-years away, while the second brightest star, 39 Leonis, is widely spaced and located to the south of the primary, and the 3rd and faintest star in the system, 35 Leonis, is to the north. Next we come to Lotto Leonis. It's a binary star system divisible in modern medium-sized backyard telescopes. Located some 79 light-years away, Lotto Leonis appears to be a yellow tinged star, with the 2 components orbiting each other every 183 Earth-years. Finally in Leo, we take a look at Tau Leonis. Visible as a double star through binoculars, it includes a yellow giant located some 621 light-years from Earth. The second star in the system, 54 Leonis, is actually a binary, a pair of blue-white stars divisible in small telescopes, located some 289 light-years from Earth. The constellation Leo also contains many galaxies, including the spiral galaxy Messier 66, as well as Messier 65 and NGC 3628, 3 of which together are known as the Leo triplet. Located some 37 million light-years away, the Leo triplet has a somewhat distorted shape due to gravitational interactions between Messier 66 and the 2 other galaxies, which are cannibalizing stars from M66. It's thought eventually the outermost stars will form a stellar stream, maybe even a dwarf galaxy, orbiting M66. Both M65 and M66 are visible in large binoculars and small telescopes, but their concentrated nuclei and elongation will only be visible through larger backyard instruments. Other bright well-known galaxies in Leo include Messier 95, Messier 96, Messier 105, and NGC 3628. M95 and M96 are both spiral galaxies, each about 20 million light-years from Earth. Both will look like fuzzy objects in small telescopes, but will show off their spectacular structures in larger instruments. M95 is the barred spiral. The other barred spiral, NGC 2903, is thought to be very similar both in shape and size to our own Milky Way galaxy. It was discovered by William Herschel in 1784. Close to the M95-M96 pair is the elliptical galaxy M105, which is also about 20 million light-years away. The constellation Leo also includes the so-called Leo Ring, a cloud of hydrogen and helium gas, orbiting 2 of the galaxies in the constellation. The gravitationally lensed object known as the cosmic horseshoe is also found in Leo. Now, looking just above Leo, you'll see the constellation Virgo, the Greek and Roman goddess for wheat and agriculture. Virgo's brightest star Spica is visible high above the western horizon. It's located some 250 light-years away. Spica is Latin for the ear of wheat, which Virgo is holding in her hand. Spica, or Alpha Virginis to use its other name, is the 16th brightest star in the night sky, and it's also both a spectroscopic binary and a rotating ellipsoidal variable. That is a close binary system whose stars are not eclipsing, but instead cause apparent fluctuations in brightness because of changes in the amount of light-emitting area visible to the observer. Spica's two main stars orbit each other every 4 Earth days, and are so close they're egg-shaped rather than spherical, resulting in them only being separated through their spectra. The primary star is a blue giant variable Beta Cepheid. It's undergoing small rapid variations in brightness because of pulsations in the star's surface. They're thought to be caused by the unusual properties of iron at temperatures of over 200,000 degrees in the stellar interior. This star contains about 10 times the Sun's mass and about 7 times its diameter. The secondary star is smaller than the primary, but still at least 7 times more massive than the Sun and at least 3.6 times the Sun's diameter. Okay, let's turn to the north now, and the constellation Bootes, the herdsman, and you should be able to see the bright orange-red star Arcturus, or Alpha Bootes, just above the northern horizon, located some 37 light-years away. It's a bloated, aging star, some 7.1 billion years old, and nearing the end of its life. Although it's not much more massive than the Sun, it's expanded out to some 25 times the Sun's diameter, and will soon puff off its outer gaseous envelope as a planetary nebula, in the process revealing its white-hot stellar core, a white dwarf, which will slowly cool over the eons of time. July also hosts 2 meteor showers, both of which will peak late in the month. The Delta Ackwards get their name because their radiant, that is the area they appear to come from, lies in the constellation Aquarius, near one of the constellation's brightest stars, Delta Aquarii. The shower originated either from the breakup of what are now the Marsden and Crack sun-grazing comets, or from the parent comet 96P Machholz. There are 2 branches to the Delta Ackwards meteor shower, southern and northern. There's the southern Delta Ackwards, visible from mid-July to mid-August each year, with peak activity occurring on the night of July the 28th or 29th. The southern Delta Ackwards are considered a strong shower, with an average of between 15 and 20 meteors per hour between midnight and dawn. Listeners in the southern hemisphere usually get the best show because the radiant is higher in the southern skies. Since the radiant is above the southern horizon, for northern hemisphere listeners, they'll see meteors fan out in all directions, east, north and west, with a few meteors even heading southwards, unless they're short and near the radiant. The northern Delta Ackwards are the weaker shower, peaking later in mid-August, with the average peak of around 10 meteors per hour. Meanwhile, the nearby slow and bright Alpha Capricornus meteor shower takes place as early as July the 15th, and will continue through to around August the 10th. This shower has infrequent but relatively bright meteors and some fireballs. It's generated as the Earth passes through the debris trail left behind by the comet 169P NEAT, which was originally identified as an asteroid, 2002 EX12. However, it was shown to be weakly active during perihelion and was thus reclassified as a comet. The meteor shower was created about 3,500 to 5,000 years ago, when about half of the parent body disintegrated and fell into dust. The dust cloud eventually evolved into Earth's orbit, causing a shower with peak rates of around 5 meteors an hour and some very bright flaring meteors, radiating out from the constellation Capricorn towards the south. Mind you, the bulk of the cometary debris won't be in Earth's path until around the 24th century. By that time, the Alpha Capricornids are expected to become a major annual meteor storm, stronger than any current annual meteor shower. And now, with more on the night skies of July, we're joined by Jonathan Nally, editor of Australian Sky and Telescope magazine.
All right, well, let's start with the view to the south. The Southern Cross is nice and high this time of year. It's standing almost upright, quite high in the south. Just to its left, there are 2 bright stars known as the 2 pointers, because if you draw a line between those 2 and extend the line out, it points more or less to the Southern Cross. The pointer star on the left, as you look at them, is the famous Alpha Centauri, which is the star system closest to our solar system. It's just over 4 light-years away. Now, Alpha Centauri is actually a double star, and there's a third, very small star nearby called Proxima Centauri. A lot of astronomers think that's actually also part of the system, so it could be a triple star system. Looking sort of broader across the sky, we've got the Milky Way, which is our galaxy seen from the inside. In the sort of mid-evening during July, Milky Way is stretching from the northeast down to the southwest. But by midnight, as the Earth has turned a bit on its axis, the Milky Way is sort of more or less lined up straight north-south. As far as planets go, well, Mars is the planet to watch this month. It reaches its closest point to the Earth at the end of July, which means that it looks a bit bigger through a telescope because it's closer. In fact, it'll look about twice the size as it did only a couple of months ago in May. That's what a little bit of proximity will do to a planet, particularly a small planet like Mars. And some of the other planets are much larger, and they always look fairly big through a telescope. But Mars, when it's further away, it looks very small through a telescope. Mars is very easy to spot in the evening sky at the moment. Just look out to the east as night falls, and you'll see a fairly bright orange-looking star. Well, that's actually the planet Mars. Higher above Mars, and still in the eastern sky, there's a bright, slightly yellow-looking star, in inverted commas. Well, that's another planet. That's Saturn. See if you can get hold of a telescope. Either you might have one yourself, or the neighbour's got one, or a friend, or whatever, or go to an observatory and have a look at Saturn through a telescope, because it really is amazing. You can see its rings, and you should be able to see a few of its moons and things. It really blows your mind away when you actually see, oh, that's really Saturn. It looks just like the pictures. What else we got? So high in the northwestern sky, sort of gone from the east now around to the northwest, is the planet Jupiter. Jupiter's the largest planet in our solar system, of course, so it seems fairly bright in the night sky because being large, it reflects a lot of light from the sun. It also has lots of moons, 69 of them at the last count, I think. A few of them are big enough to be spotted through binoculars. There are 3 or 4 of them you can see through binoculars, depending on the size of your binoculars. Just a normal pair of 7x50s is perfectly fine to see these little moons. So over in the west, as the evening twilight is beginning, you'll see a very bright-looking star. Again, that's star in inverted commas, because this is the planet Venus. You just can't miss it. I mean, it's really big and bright. Basically, only the moon and the sun are brighter in the sky than Venus when it's at its brightest. People look out and think, what on earth is that bright star? Well, that's actually Venus. Now, if you're an early riser, everything we've spoken about so far is in the evening. If you're an early riser, though, and you're up around about 6 a.m., you will see the Milky Way is nowhere to be seen anymore. It's dropped below the western horizon as the Earth has turned. So the sky isn't quite as full of as many stars as it was in the evening, because a lot of the bright stars are along or near the stretch of the Milky Way. Just coming up over the eastern horizon, though, before dawn out there in the morning, are the really distinctive stars of the constellation Orion, the Hunter. And you should also see, not far above the horizon, the star Sirius, which is the brightest star in the night sky.
That's Jonathan Alley, the editor of Australian Sky and Telescope magazine. You're listening to Space Time. I'm Stuart Gary, and that's the show for now. You can subscribe and download Space Time as a free twice-weekly podcast through Apple Podcast iTunes, Stitcher, Bytes.com, Pocket Casts, SoundCloud, YouTube, Audio Boom, from spacetimewithstuartgary.com, or from your favorite podcast download provider. Spacetime's also broadcast coast to coast across the United States on Science 360 Radio by the National Science Foundation in Washington, D.C., and available around the world on TuneIn Radio. If you want more Spacetime, check out our blog where you'll find all the stuff we couldn't fit in the show, as well as loads of images, news stories, videos, and things on the web I find interesting or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word and in lowercase, and that's Tumblr without the E. You can also follow us on Twitter through @StuartGary, at Spacetime with Stuart Gary on Instagram, and on Facebook, just go to www.facebook.com/Spacetime with Stuart Gary. Spacetime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe.
You've been listening to Spacetime with Stuart Gary. This has been another quality podcast production from Bytes.com.